Imagine this. You wake up tomorrow morning, check your phone, and see a headline that changes everything we know about the universe. Faster than light travel is possible. Your coffee nearly drops from your hand. The stars that seemed forever out of reach, those distant galaxies we've only seen through telescopes, those exoplanets that might harbor life. Suddenly, they're not just pictures in textbooks anymore. They're destinations, real places we could actually visit within a human lifetime. Now, before you start packing your bags for Alpha Centauri, let me tell you something that's going to blow your mind even more than that headline. Recent developments in theoretical physics have brought us closer to this reality than ever before. We're not talking about science fiction anymore. We're talking about actual scientists with actual equations, publishing actual papers in peer-reviewed journals, proposing mechanisms that could potentially break what we thought was the ultimate cosmic speed limit. The universe has been playing hard to get for billions of years, but we humans, we're persistent creatures. We've gone from riding horses to landing on the moon in less than a century. So the question isn't really, can we travel faster than light? The question is, what's really happening in physics laboratories right now that's making this conversation possible? Stick with me for the next few minutes, because what you're about to hear will fundamentally change how you think about space, time, and humanity's future among the stars. When we talk about faster than light travel, we first need to understand why light speed became the ultimate barrier in the first place. Back in 1905, a patent clerk forever changed our understanding of reality by introducing the special theory of relativity. And 10 years later, the general theory of relativity completed this revolutionary framework. These theories didn't just suggest that light speed was fast, they declared it as the absolute cosmic speed limit, approximately 299,792,458 meters per second. But here's what makes this truly fascinating. It's not about light being special in itself. Light travels at this speed because it has no mass. The real limit is about information, causality, and the fabric of space-time itself. According to relativity, as an object with mass accelerates closer to light speed, something bizarre happens. The object's mass effectively increases, requiring exponentially more energy to accelerate further. Time slows down for the moving object relative to stationary observers, and lengths contract in the direction of motion. If you somehow reached light speed, you'd need infinite energy. Your mass would become infinite, and time would stop completely. This isn't just theoretical mathematics on a chalkboard. We've verified these effects countless times. Particle accelerators push subatomic particles to 99.99990% of light speed. These predicted effects must account for relativistic time dilation, or they'd give you directions to the wrong location. Muons created in Earth's upper atmosphere by cosmic rays shouldn't reach the surface based on their decay rates, but time dilation allows them to survive the journey. The cosmic speed limit isn't a suggestion from the universe. It's been tested, verified, and confirmed through decades of experimental evidence. Now, here's where things get interesting, and where science fiction starts shaking hands with theoretical physics. In 1994, a Mexican theoretical physicist named Miguel Alcubierre asked a brilliant question: what if we don't move through space at all? What if we move space itself? His mathematical model, published in a legitimate physics journal, describes something that sounds absolutely wild, but is completely consistent with Einstein's equations. Imagine space-time as a flexible fabric. Because it literally is. Alcubierre proposed creating a bubble around a spacecraft where space-time contracts in front of the ship and expands behind it. The ship itself isn't moving through space. It's riding a wave of space-time like a surfer rides an ocean wave. Inside the bubble, space-time remains flat and normal, so the ship never actually exceeds light speed locally. You're not breaking the cosmic speed limit, you're exploiting a loophole written into the equations of general relativity itself. Think of it like a treadmill. If you're walking backward on a treadmill at 3 miles per hour, but the treadmill is moving forward at 10 miles per hour, You're moving forward at 7 miles per hour without actually walking forward. The Alcubierre drive does something similar with space-time. The mathematics work. The physics don't violate relativity. On paper, you could theoretically travel from Earth to Proxima Centauri, our nearest stellar neighbor at over 4 light-years away, in weeks or months instead of tens of thousands of years. The equations don't just permit this, they describe exactly how it could function. This isn't pseudoscience or wishful thinking, this is legitimate physics based on our best understanding of how space-time operates, published in peer-reviewed journals and taken seriously by physicists worldwide. What's changed recently that's bringing faster-than-light travel from the realm of pure theory into potentially achievable engineering? Several developments have scientists genuinely excited. First, researchers have been refining the Alcubierre model, finding modified versions that are less energetically demanding than the original proposal. A 2021 paper introduced a model called the constant velocity subliminal warp drive that doesn't require exotic matter with negative energy density, at least not as much. Then there's the work being done on understanding negative energy itself. Quantum field theory predicts something called the Casimir effect, where two metal plates placed extremely close together in a vacuum will attract each other because they're excluding certain quantum fluctuations from the space between them. This creates a region with less energy than empty space, effectively negative energy. We've measured this effect experimentally. It's real. Researchers are exploring whether we can generate, control, and scale up these negative energy conditions. Additionally, advances in metamaterials, engineered materials with properties not found in nature, have shown we can manipulate electromagnetic fields in unprecedented ways, creating effects like negative refraction. While this isn't the same as manipulating space-time, it demonstrates our growing ability to engineer reality at fundamental levels. Computational power has also exploded, allowing physicists to run complex simulations of warp field geometries that would have been impossible decades ago. These simulations are revealing configurations and approaches that might reduce the astronomical energy requirements. Furthermore, our understanding of quantum mechanics and general relativity continues to deepen. While we don't yet have a complete theory of quantum gravity, insights from string theory, loop quantum gravity, and other approaches are providing new mathematical tools to explore space-time manipulation. Now let's talk about the elephant in the room, or more accurately, the Jupiter mass energy requirement in the room. When Alcubierre first published his warp drive concept, calculations suggested you'd need negative energy equivalent to the mass energy of Jupiter to create and maintain the warp bubble. To put that in perspective, that's about 1.910 volume 27 kilograms converted entirely to energy according to Einstein's famous equation, EMC2. The entire energy output of the sun over millions of years wouldn't be sufficient. Humanity's total annual energy consumption is essentially a rounding error compared to this requirement. You'd need to harvest and convert more matter than exists in most planetary systems. Even if we could somehow generate this energy, there's the engineering challenge of how to create the specific space-time geometry required. We're talking about precisely manipulating the fundamental fabric of reality itself with extraordinary precision across significant volumes of space. Then there's the exotic matter problem. Most warp drive models require matter with negative mass or negative energy density, which we've never observed existing naturally in quantities larger than quantum fluctuations. Creating, containing, and controlling such exotic matter presents challenges we can't yet solve. There are also concerns about what happens when you turn the drive off. Some calculations suggest that particles and radiation accumulated in the warp field during travel might be released as a devastating blast of energy when the bubble collapses. Imagine arriving at your destination and inadvertently sterilizing it with a gamma-ray burst. Another puzzle. Inside a warp bubble, you might be causally disconnected from the outside universe, making course corrections impossible. How do you steer something that's fundamentally isolated from the space it's traveling through? These aren't minor technical hurdles. They're fundamental challenges that push the absolute limits of physics and engineering. To truly understand the possibilities and limitations of faster than light travel, we need to talk about the strange marriage between quantum mechanics and general relativity. These two pillars of modern physics describe reality with extraordinary accuracy, yet they speak different mathematical languages and make fundamentally different assumptions about how the universe works. General relativity treats space-time as smooth and continuous, while quantum mechanics describes reality as fundamentally granular and probabilistic at the smallest scales. Where these theories intersect at scales incredibly tiny and energies incredibly vast, we enter territory where neither theory alone gives us complete answers. This is where concepts like quantum foam emerge, suggesting that at the Planck scale, around 10 AE 35 meters, space-time itself might be bubbling with temporary fluctuations, constantly creating and destroying tiny wormholes and distortions. Some physicists propose that understanding and potentially manipulating these quantum space-time fluctuations could be key to engineering warp drives or wormholes. Quantum entanglement, where particles remain connected across any distance, already demonstrates that quantum mechanics permits correlations that seem to transcend space. While entanglement doesn't transmit information faster than light in ways that violate causality, it reveals that quantum reality operates under different rules than our everyday experience suggests. There's also the concept of quantum tunneling, where particles can pass through energy barriers that classical physics says should be impenetrable. If space-time itself has quantum properties, might there be analogous tunneling through space-time? Recent developments in quantum field theory and curved space-time have shown that accelerating observers experience empty space differently than stationary observers, seeing particles where others see vacuum. This Unruh effect, along with the similar Hawking radiation from black holes, demonstrates that space-time geometry and quantum fields are intimately connected in ways we're still exploring. Let's imagine for a moment that we actually achieve faster-than-light travel, even if it's a century or more away. What would this mean for humanity's future? The psychological shift alone would be profound. Currently, we're essentially trapped in our solar system. Mars is the best candidate for colonization, and it's still a harsh, radiation-soaked desert that would require tremendous resources to make barely habitable. The nearest star system with potentially habitable planets would take tens of thousands of years to reach with conventional propulsion. We're cosmic homebodies not by choice but by physics. Faster-than-light travel would fundamentally change this equation. Suddenly, the thousands of exoplanets we've discovered wouldn't just be catalog entries, they'd be potential new homes. The galaxy would transform from a pretty backdrop into an actual neighborhood we could explore. The scientific implications are staggering. We could study extreme physics environments directly, observe phenomena from multiple perspectives across vast distances, and potentially contact other civilizations if they exist. The economic possibilities are equally dramatic. Asteroid mining becomes trivial when you can reach the asteroid belt in minutes. Resources from other star systems could become accessible. The very concept of scarcity might need to be reconsidered. Philosophically and culturally, faster-than-light travel would force us to mature as a species. We'd stop thinking of ourselves as Earthlings and start identifying as galactic citizens. Our art, literature, politics, and religions would all evolve to accommodate this expanded perspective. However, there are darker possibilities too. The same technology that enables exploration could enable unprecedented warfare. Conflicts could span star systems. The ethical questions about how we interact with alien ecosystems or potential civilizations would be urgent rather than theoretical. Thank you for staying with me on this journey through the cutting edge of physics and human possibility. The fact that you've listened to these ideas, engaged with these concepts, and allowed yourself to wonder about humanity's future among the stars means you're part of this grand adventure too. You don't need to be a physicist to contribute to humanity's greatest journey. You just need to maintain that sense of wonder, to ask questions, to stay curious about the universe and our place within it. To the students and young scientists among you, good luck in your studies. The problems we've discussed today are waiting for your generation to solve them. The equations that will unlock faster-than-light travel, if it's possible at all, might be written by someone watching this right now. To the educators, good luck in inspiring the next generation to look up, to question, to calculate, and to dream big. To everyone else, good luck in maintaining your curiosity about this incredible universe we inhabit. Keep looking up, keep asking questions, keep pushing the boundaries of what's possible. The stars are waiting, and whether we reach them in decades or centuries, the journey begins with conversations exactly like this one. Thank you for being part of it, and may your own journey through this cosmos, whether literal or metaphorical, be filled with discovery and wonder. Clear skies and good luck to you all.